Yes,
مس بليز
yes,
كرمال الدراج والليفت.
yes.
أنا ما عندي فكرة بالمرة عنهم، فإذا ممكن بس هيك شوي
Okay,
توضحين لنا الموضوع.
sure, sure. If you have a flow over, so let me draw a shape for you. Look, if you have any shape, okay, and you have a flow over this shape, you, we have a flow field flowing over it, okay. When the flow will go over the shape, it will do separation, okay. So
أوكي.
because it will hit the body, it will do separation, which will result in change in direction of the flow field, okay. So what we do is that we consider that if we take the fluid around the body, okay, and we compute the resultant force acting on the body from the fluid on the body, okay, because as a fluid will move over the body, it will cause a certain action on it, okay. This
أوكي.
action of the fluid on the body, so the action force of the fluid on the body can be divided into two components. Can be divided into two components. Okay? These components are called drag force, and lift force. Okay?
أوكي.
What does this mean? You have these two components are one along the direction. So the drag force is defined as the force in the same direction of the flow, in the same direction of the flow, okay? And the lift force is the component of the force in the direction perpendicular to the flow. So, and lift force is defined in the direction that is perpendicular to the flow. Okay?
أوكي.
So here, for example, if you go to the example of the sphere, because the sphere is symmetrical, if you do the resultant, you will not have a resultant force in this direction. Due to symmetry, the components will cancel out in this direction. So no net lift force, but you'll have a net drag force, because imagine that the flow will go over a sphere, it will tend to move it in the direction of motion of the flow. Okay, so here you will only have drag and no lift because the sphere is symmetric. But in the case of turbine, if you look at the figure here, you have the flow of air going over the turbine blades. What will happen, because it's not a symmetrical shape, okay, and plus you might have an angle of attack, and if the flow is not horizontal, also this will create lift. So here, for example, here, if you have, let's say, for the airfoil, if you have a certain angle of attack, you will not have symmetry anymore, and this will cause lift and drag. Okay, so as you can see here, because we have a non-symmetrical shape, so of course we will have lift and drag. You have that the drag is in the direction of the flow, and the lift is perpendicular to the flow direction of the flow. And the lift is important for us here because it is perpendicular to the blade of turbine, so it will be able to cause rotation. However, the drag will not contribute to rotation because it's parallel to the blade.
Okay, and you said because إنه في flow أكتر above the blade أو pressure above the blade, the
Yes.
air will lift the wing يعني أو شيء.
Yes.
اوكي
Yes.
ليضل في equilibrium يعني. اوكي.
Okay.
Yes. Okay. Thank you.
Well, okay. So here we were talking about the energy, the power available in a volume of air fluid flowing through a cross-sectional area A. Okay, so we said that if we have a certain cross-sectional area, this is A, and we have a fluid moving through this area, this fluid will carry power. Okay, to compute the amount of power carried by this fluid, the power is equal to, we can calculate it as force times volume, okay, times volumetric flow rate. So it can be predicted as we said. So for power, you have several ways to calculate it. Okay, you can do it force times velocity, V. Okay, in this case, the unit of the force will be in Newton. The unit of velocity will be in meter per second. But this formula is used if you are displacing, let's say, a certain body at a velocity, at a known velocity V. If you have, and on the other hand here, what we have is the pressure. So if you have a pressure is Newton per meter square. Okay, then to obtain the unit of power, you should multiply by what? Should multiply by the volumetric flow rate, Q dot. So we should multiply by Q. I put Q dot because it's a rate. Okay, and its unit is meter cube per second. Okay, and we know that the dynamic pressure of a fluid moving is half rho u square, and the volumetric flow rate, if we have a flow over a cross-sectional area A, the volumetric flow rate is U times A. Okay, so in total, we will have that the power carried by this fluid is half rho U cube times the cross-sectional area. So you can see here that higher is the velocity, higher will be the power, and the velocity has a big impact because it's to the power cube. Okay, so much more power is available at higher speeds. So of course, if we have a zone with high wind speeds, it will be more efficient to put wind turbines. So always to select a land for wind turbines, we try to have a location where the velocity is very high, the velocity of winds. Now, we have seen together that if we can, we should try to extract the maximum possible power from wind turbines, okay, from wind. But we will see here that it is never possible to extract all the power. So if we have a fluid moving at a certain velocity u, we cannot extract 100% the power. So we cannot obtain the power calculated in the previous slide, which is half rho times A times U cube. Okay? Why? To understand why, we will do a small analysis. So here just they are telling us that some of the kinetic energy that is carried downstream of the wind turbine in order to maintain the air flow. What do we mean by this? We mean that we should lose one part to make our flow go through the turbine blade. So to understand this effect, if you look at this figure, for example, this is your turbine. Okay, you have a flow going over the turbine, but you need to have operation. You should have a flow getting out from your turbine. Okay, so it's circulating over the turbine blade, and because you need a proportion that to get out, so you need some kind to lose. You will need to lose some kinetic energy that is carried downstream of the wind turbine in order to maintain flow motion. Okay, due to this effect, it's not possible to use the whole wind energy, the whole energy provided by the flow moving through the turbine. But we can calculate that the maximum theoretical efficiency, known as the Betz limit for extracting power from the wind, is equal to 59%. And we will do together a small analysis. Of course, look, you are not responsible of such complicated analysis, but just I want you to see how we derive this ratio, 59%. Okay, but don't worry, you are not responsible of such things. It's a little bit complex, but because it might interest a major part of you, I will explain it. Okay, but don't worry about it. Just understand the explanation. But I will not expect from you to do such derivations. Okay, so what is the idea here? The idea is that when we have wind going through the blades, we can consider that wind will go first through a certain we have an upstream velocity. Okay, so the wind is coming, it will hit, let's say, a certain cross-sectional area A0. Then when flowing within the turbine blades, it will go over a cross-sectional area A1, and it will be ejected through a cross-sectional area A2. But if we do a certain design such that A0 is the highest cross-sectional area, and A2 is the larger, A0 the smallest cross-sectional area, A2 the highest cross-sectional area, this will lead to the higher velocity, at which level U0 will be the highest velocity. Okay, because you know that from conservation of mass, Q is constant. Of course, if you consider incompressible fluids. Okay, so we can assume here that air can be treated as incompressible if Mach number is not very high. So we can say that U0 A0 is equal to U1 A1 is equal to U2 A2. Okay, and we will demonstrate together that we will, in order to not lose a lot of energy, we need to reduce U2. So to reduce U2, we can increase the exit cross-sectional area. Now, what will happen when air will flow through the blades of the turbine? We need to compute what is the power we will extract. Okay, to compute the power that we will extract, as we have seen before, we can calculate it in two ways. Or we can say that it is the pressure times the volumetric flow rate. And another method to calculate the power is the force times the velocity. Okay, so at the level of the turbine, we will extract a power equal to the force on the blades times the velocity of air going through the blades, which is U1. Okay, so we can write that the pressure that we will extract through the turbine, the power that we will extract through the turbine, is equal to the force F on the turbine, okay, times U1, which is the velocity of the air going through the blades. Now, how to calculate the force F? The force F can be given by the following relation, which is called linear momentum. Okay, and as I told you, I don't expect you to know these relations. Okay, but just for some, it might be interesting. This is why I am explaining it. So, for mechanical engineers, you know that F is, if you apply linear momentum, it's m dot u out minus u exit minus u inlet. Okay, so here, if you consider your figure, you have, what is m dot? The mass flow rate. The mass flow rate can be calculated as rho times u0 a0 or rho times u1 a1, because they are equal. Okay, times what? Times the velocity at the inlet upstream. So before, if you want to understand what is upstream and downstream, when you have wind, imagine that you have wind. Your wind first is coming, let's say like this, but due to when it will face the turbine, it will do separation. So because you know, when a fluid will hit anybody, it will do separation. So due to separation of the fluid, this will induce a new area over the turbine, which is A1. And if you follow the fluid flow after, at the exit, you can consider that when reaching the fully developed state, you have, this is the downstream area. And the downstream area is the highest one, okay? So the force can be computed as m dot times u out minus un. U out is the outlet velocity is u2 and the inlet velocity is u0, okay? So you have it times here in real case, okay? So it's times, so times u0 times u0 minus u2, okay? So this will give us the expression of the force. And when we multiply the force by u1, okay, we will get the power. So the power is F times u1 equals to rho u1 squared times a1 times u0 minus u2. So this is the power that we can extract from, this is the power that can be extracted from the turbine, okay? Just one notice, when you put m dot u out un, you find the force of the turbine on air, okay? But what you want is the force of the air on the turbine. This is why you will take the opposite. So here, if you want, I will just put minus before it. Minus m dot u out minus un, which is plus m dot un minus u out. Because what you are interested in, the force F represents the force. This is the force of air on turbine. Okay? So just now we have developed the expression of this force. Now, and the power it will induce is the force times the velocity of air going through the turbine, which is u1. Now, you know that the power is, you can express it in a different way, because the power is due to what? If you remember from chapter 3 we have seen together, the power, which is a type of work, is produced, can be produced from variation in kinetic energy. So another way to write the power is to say that the power results from the variation of kinetic energy. Of course, here we assume what? We assume that we don't have loss of heat. Okay, so Q is 0. And for the internal energy here, delta U, we can consider that variation of internal energy is due to variation in kinetic energy, okay? Because no potential energy variation, and we consider no enthalpy variation. So the main variation is due to variation in kinetic energy. Therefore, another way to find the expression of the power is to say that it's equal to the variation of kinetic energy. And therefore, if we write this, the power can be computed as half rho u1 a1 times u0 square minus u2 square. So now you obtain two expressions of the power. And if you equate them, if you equate these two relations, okay, you can get a relation between the three velocities, u1, u2, and u0, okay? And now, if you replace u2 by its expression here, back, you replace it back u2 in this expression, you can get the power extracted function of u0 and u1, which is the upstream velocity and the velocity going through the turbine. Now, all I did here is just for you to understand the final step, okay? Now, because what interests me is to see that I cannot extract the maximum power from the wind. I cannot take all the energy, because one part will be lost. As we said, one part will be lost due to the exit, okay? Because you need to exit your flow, so you need a certain kinetic energy exiting your system. This is why you cannot extract all the power inside the air coming. Now, if you want to find what is the maximum amount that you can extract, you will use this formula, okay? If you use it in this slide here, we have developed together the power function of u0 and u1, okay? But we know that u1 is smaller than u0, because we said that the upstream velocity, which is u0, is the highest one. Then u1 is smaller, then u2 will be the smallest one. So since u1 is smaller than u0, we can set u1 equal to 1 minus a certain value of a between 0 and 1 times u0. And then if we plug u1 in terms of u0 inside the power relation, we get the following. Okay? So it's a simple replacement. We get the power equation. Now, from this equation, what can we conclude? First, this is the maximum power we can get. It is the power that is coming through our turbine. Okay, we have seen that if we have a flow coming at a certain velocity through a certain area, this is the maximum power it can give me. But this power is multiplied by a certain factor, and this factor depends on A, and A varies between 0 and 1. If we do a small study on this factor, as you observe here, if we study this product for different values of A, we can see that the maximum possible value for this factor is nearly 0.59. This is why we say that the maximum power we can extract is 59% of the power that is coming. Okay, because as we have seen, we need to lose a certain kinetic energy to have the system working. Okay, because we should have a flow downstream to operate the wind, because the wind turbine, because it will continuously work. So flow will go in and flow will go out. Okay, so the maximum that we can extract is nearly 60% or 59%, which is a great amount. Okay, because we know that the wind energy is largely available, and if we can extract 59%, it will be ideal. And of course, in real cases, we will use less than 59%, because you know that always in reality, we have losses. Okay, but at least if we have, let's say, 30, 40%, if we extract 30 or 40% of the wind energy, then we can produce a huge amount of energy that can be used to replace all other techniques, because wind is widely available. So if we maximize our profit from it, we can, if you want, use only wind energy and no need to use fossil fuels, no need to use any other sources. Of course, if we are in a location where wind energy is available. So, as a conclusion now, okay, this is the general relation that will give you the wind power in a turbine. So here, you should know this relation and you should know how to apply. So I will explain each term. Okay, so you have rho AV cube. So already this is what half rho AV cube. This is the maximum. So this with this, let's say, this represents the maximum I can extract. Okay, so this term is the maximum power. It's the power carried, if you want, not the maximum, the power carried by the airflow. Now, so this is the power carried by the moving airflow. Now, when I multiply, but as we said, we cannot take the whole power, we can take a maximum percentage of 59. This is why we multiply by what we call, so we should multiply first by the coefficient of performance, which should be lower than the BETS limit. So maximum it's 59, 0.59. But in reality, as we said, it's between 30, 40. So let's say 35% will be fine. So when we multiply by the coefficient of performance, this will, once we multiply by CP, then this is the power that is extracted. So when we multiply by CP, so by multiplying by CP, we get the power extracted by the wind turbine. But still we are not done. Why still we are not done? Because you know, after the turbine will take this power, we have some losses. Okay, why? Because first we need to go through the generator, okay, to produce electricity, and the generator has a certain efficiency. It's not 100%. So after finding the power extracted by the turbine, by multiplying by CP, we should then multiply by the efficiency of the generator, okay, because at the end what is important for us is the power that we use. The power that we use will be after the generation of electricity, and also after, if you want the whole path, then we multiply also by gearbox and bearing efficiencies, because these are present within our turbine. We have inside, as we have seen, we have a box containing the gearbox, the bearings, which will help to transfer the mechanical energy into rotation, and then we have the rotation that will be transformed into generator into electricity. So this is why we should multiply by all of these efficiencies to get at the end the total power used. So when we multiply by all of these efficiencies, generator efficiency and the gearbox and bearings efficiency, then we can get the used power, the useful produced power. Okay, so this is the useful produced power. Okay, now we will look at the economical side of wind power.
Bess, can I ask a question?
Yes, sure.
The CP,
Yes.
how do we physically optimize it?
Sorry, it's very,
what
it's lagging a lot. Can you type it in the chat?
Yes.
I cannot hear you. Yalla, I'm waiting for you. Type your question. Type your question. Yes, what about the coefficient of performance? Okay. To design for it, this will depend on the geometry. So we play with the geometry of the blades, okay? And we do experimental work on it to see which geometry will give me the maximum coefficients of performance, okay? So it's mainly the geometry, it's also the orientation of the blades, because you have a certain system, you have a certain the yaw control system, which will change the direction of your blades in order to optimize this coefficient. Okay. So now we will talk about wind power economics. Yes.
I'm sorry for being late with my question, بس كان بس بدي أسأل عن الليمت هي كرمال ما يصير stall يعني؟
الليمت لا، الليمت يس، يعني إذا بدك تيصير في flow over the turbine، يعني أنت when you have a flow entering ما فيك تخليه كله جوا، يعني you have to have a continuous flow. Air should go out and then a new part should go in. يعني to maintain this flow over the wind turbine, you should have a certain loss of kinetic energy.
Okay.
ولا ما بيصير في flow. Okay.
Yes.
Okay. So now we will talk about the economics of wind turbines. Okay, we have seen that wind is largely available and present a very important future if we know how to use it. This is why turbine technology is in constant improvement. We are designing larger turbines to produce higher power. We are getting more specialized in blade design, because as we have seen, the geometry of the blade will affect a lot the performance of the turbine. Plus, the blade should support the high constraints, because you know that you have wind acting on it, and it will be subjected to several rotations. So it should if you want sustain fatigue, it should sustain crack. It should be, and it should be mechanically very powerful to sustain, to resist to the cycles of rotation and to resist to the wind action. So we have a whole research field on the materials from which should be done the blade. Okay, so this is a research field alone, the material properties of blades used in wind turbines. In addition, turbine technology is very important in power electronics, because it can lead to it will produce a large amount of power. Plus, we are using computer modeling to produce more efficient design, because as we have seen, we have a system that will control the orientation of the turbine in a way to optimize its performance. Because so this system, this computer modeling system, will take as inputs, if you want, the wind velocity, the wind direction, and based on this, it will optimize what should be the blade directions to extract the maximum power. So this will require advances in computer modeling technology. Plus, we have manufacturing improvements in the way of manufacturing the turbine components. Okay, so as you can see, we have a lot of fields that are involved in the turbine technology. And the wind technology success is very clear, because we can see that with time, what is happening is that the cost of energy produced by wind is reduced, while the capacity at the planet is increasing. So with time, because we are advancing in technologies, these advances will lead to a higher production. So we will have a larger amount of capacity for wind turbines, and due to this, we can reduce the cost per kilowatt hour, because you know, when you have a certain business that is growing very fast, then you can allow for reduced costs. Okay, so from this graph, it is clear that we have the wind turbine sector is very is an improvement, in continuous improvement, because we are able to reduce the cost of energy per kilowatt hour, and at the same time we are increasing the capacity. Now, how to improve the capacity factor? So this is one of the questions which was asked. So for the capacity factor, we can do several things. First, we can choose a good location where the velocity of wind is high. Okay. Plus, we can play with the geometry of the element of the turbine, of the blades of the turbine. We can use larger turbines to increase the energy capture. We can choose a better location, so better sitting, by choosing a good location and good orientation for the wind blades. We can optimize more this factor. So all of these technology advances can increase the capacity factor for the turbines. Now, with time, the size of the turbines was largely increased. So we went from small to very large turbines, because we will see that larger is the turbine, larger is the power we can extract from. So technically, we have, in general, 2 to 3 moving parts. So we can have more than 3 blades, but it's the 3 blades was shown to be the most efficient, because you will reduce the weight in this way, and at the same time you can obtain a very good performance. So the majority of wind turbines are designed based on 3 blades. And this design required very low maintenance and present a good performance.
على السي بي.
Yes.
You said that if you put it in places where the wind level is high,
Yeah.
then it will make it better. But here it's not simply relative to the wind speed. يعني إذا كان high or low ما لازم يأثر على ال percentage.
Yes, I see what you mean. Yes. Look,
Doctor-
what they mean, if you want here, that when you have, it's more related more than what when I said large speed, I wanted to say if you want orientation, because sometimes, let's say, if you have high winds, okay, high wind velocity, you can't يعني ما بيقعد في recirculation of wind. So let us say, for example, when you have a high velocity wind بيصير في مثل unidirectional. Okay, so this will help you to have it perpendicular to your to the blade of your turbine. And هي أكتر related to the direction مش to the velocity magnitude. Okay, لأنه بس يكون عندك small wind ما بيكون في small momentum, it will tend to, if you want, not go straight, يعني do recirculation or not reach in an effective way. Okay, but when you have a high wind speed, it will overcome a resistance of air, so you can obtain a unidirectional flow. And the unidirectional flow, if you direct appropriately your blade, this will help into leading to a better coefficient of performance. This is why they are talking about the setting. So it's true that the magnitude, as you said, مش هي ال directly حتأثر على ال CP. But when you have high wind speeds, يعني you can ensure a unidirectional flow that can hit your blade in an appropriate way without being resisted by the obstacles or air.
دكتور وكمان مش ال larger turbines allow for a larger blade diameter.
بلى صح.
فانه كل ما كبرون كل ما بيقدروا يستعملوا blades اكبر بلا ما يعطلوا هم ال circulation.
Of course. Okay. أكيد وقت يحكوا ب larger turbine, it's a higher diameter, yes, and it's a higher height كمان. يعني when you have a higher height, you can avoid يعني ما بيقعد عندك ال effect of obstacles. يعني بيصيروا كل ال obstacles تقريبا تحت ال wind, and this will ensure a better unidirectional flow that will hit your blades. Okay. Any other question on this? So now we will talk about the design of farms of wind turbines. So when we want to design a wind farm, we should answer the following questions. First, we should see where is the best location for a wind farm. And of course, when we talk about the location, we should look at many aspects. First, we should have a zone where we have high wind speeds. Okay. Second, we should look at a zone that is far from a population, because we want to avoid noise, and we need to have a large space available, because as we have seen, we need a large amount of wind turbines to produce a sufficient power. So this is for the